will continue our discussion on fault detection in rotating machineries. As you know, gears are again a very important component apart from bearings, and in the industry, in many of the equipment, we have a prime mover, which is usually an electric motor and an IC engine. And as you know, the IC engines, they usually have a speed of range of operation anywhere from a low speed diesel engines from 500 rpm to maybe 3000 or 4000 rpm. Similarly, a petrol engine may be a little higher rpm till about 6000 rpm, the normal engines which one uses. And then if you talk about electric motors, it of course the speed depends on the pole pairs in the electric motor, but we can have speed variations anywhere from the 1400 rpm or 1500 rpm to 3000 rpm, depending again on the pole pair. For a 2-pole electric motor running at a supply frequency of 50 hertz, we will have the speed as 3000 rpm and so on. So, the prime mover speeds typically from 500 rpm maybe to 6000 rpm. Okay. This is what happens, but the mechanical unit which are being moved by this prime mover may have a requirement of another speed. Like in the case of a cement plant, the kiln maybe rotates only at 3 rpm. Okay. In automobiles, we require different speed ratios, speeds. So, we need to have different gear ratios. We need to have different speed ratios because of the dynamics requirement of the automobile. I am not going to go into the details of the dynamic requirements. So, in this class, we will focus on gears and how exactly we can find out defects in gears. So, to bring about such a speed reduction or speed amplifications, one needs to have a gearbox in between. So, gearbox forms a vital component in any mechanical plant or industry. And another complicated problem is the power direction. Sometimes the power is inline, sometimes I need to have the power direction changed. So, this forms that the speed reduction will be there, and as you know from the law of gearing, if I have a pinion meshing with the gear, the pinion has a diameter d1 and its speed is n1. This has a speed d2 and speed n2, where speed n2 means the rotational speed. So, d1 times n1 will be equal to d2 times n2, because the linear velocity at this point has to be the same, that is from the law of gearing. Okay. So, I can bring about a speed ratio depending on the diameter, or that boils down to how many teeth I can have in a gear. So, the gears are meshing, the driven one is the pinion or the driven one is the gear. From the gear dynamics, this has to be maintained, okay, or T1 times N1 is equal to T2 times N2. And then there are gearboxes, depending on the type of gear, okay, depending on certain profile of the gear tooth. Okay. Gears tooths are meshing. I am just drawing one tooth. So, they have to have certain profile. The gear profile is usually an involute. Okay. And these gears are carrying certain loads. So, this gear tooth which are in mesh will be subjected to contact stresses here. So, we put a layer of lubricant, there is a lubricant, because there is heat generation because of contact, and then lubricant is there because of contact, the area will be stressed and there will be wearing out of the profile. So, a gear under load will be subjected to wearing load, will be subjected to wear of the tooth flank, wear of the flank of the gear, stresses on the root will develop, and then will of course, lubricant can again bake, like the example of gear, like the example of bearings which we discussed about. So, all these conditions can happen, and on top of it imperfect manufacturing. In terms of the transmission error, that means there are radial clearances in the bearing which are in the gears which are meshing against each other. So, all these conditions happen, and in the normal operations of a gear these get complicated and so on. So, if I have a gearbox, and as you know, suppose this is a gearbox, this is my input shaft, there could be an intermediate shaft and there could be an output shaft. And so on, this could be happening. Okay. So, these gear ratios, depending on the teeth ratios, the speed, output speed will vary, and there are bearings supporting the shafts. Okay, and they are on the foundation. So, this is a gearbox. On top of it, this gear, there is lubricant in the gear. So, wear and tear will happen, and then these things will happen. And this is a multi-stage gearbox, there could be change in the direction and so on. So, I will give you an example of an automobile gearbox. This is how it looks in the inside. So, one is an input shaft with a gear, and this is the lay shaft. Depending on the gear you shift, these gears would shift, and then the corresponding speed ratios would be selected. So, you could be having a gear shifter which will change the meshing gears. So, and then you can have a first gear, second gear, third gear, fourth gear and so on, or a reversing gear. And then of course, this is a spur gear and this is a helical gear and so on. So, helical gears make a nice smooth contact as opposed to spur gears, and no matter what, these gears are having a gearbox, there is a lot of lubricant to take the heat away, and some of the gearboxes, which we in our study, what we did is, this is a healthy gear, and if you can see this, we had one tooth removed and two teeth broken in these gears by for our experimental study. And how do you detect faults in gears? One, of course, there are many methods now. One is vibration monitoring, which we will focus this class on. And another technique which has emerged out of the research at IIT Kharagpur is using motor current signature analysis, which we will discuss subsequently later on in perhaps next week, and then looking at the wear debris analysis. This will basically look at the condition of the lubricant in the gearbox, and even to some extent we are looking into thermography. So, traditionally vibration monitoring was being used to measure the vibrations of a gearbox, and analyzing them in the time domain, in the frequency domain, we can find out the faults in the gearbox. And while discussing subsystem analysis, I did mention that how subsystem analysis can be used to find out and identify the defects in the gearboxes, and then vibration monitoring with some signal processing technique. Like coherence analysis. So, in this class I will focus mostly on the vibration monitoring aspect, and then later on we will see how motor current signature analysis, wear debris analysis, thermography can be used, because as I was giving you examples earlier also, say I have a large windmill, okay, mount on a, and then there is a gearbox here. So, how do I monitor the condition of such a gearbox, which is maybe 100 meters from the ground? So, this calls for using techniques like MCSA or even period thermal inspection by using a drone camera, drone IR camera. So, these are some of the latest techniques which are happening for monitoring gearboxes. And another, particularly today, now people are talking about electric vehicles. Okay. In electric vehicles, we have a motor, and you can have a speed controller of the motor, or you can have a mechanical gearbox. Okay. Of course, the battery is the major component in an electric vehicle. So, how do you monitor the gearbox of such electric vehicle? And MCSA is a good area by which MCA motor vibration can be done. And this is another, that same fault simulator which we have in the laboratory. We have a planetary gearbox, okay, and you can find out the faults in such planetary gearbox by measuring the vibrations, and this is pulley driven, and there is a load clutch which gives some load on the gearbox, and you can measure the vibrations on the gearbox for varying load, etc. So, gearboxes could be can also have a planetary gearbox. So, we will see, if you go to my book, you will see the equations which give you the characteristic frequencies of bearings of gears in a planetary gearboxes. And I will not discuss planetary gearboxes per se, but going back to my example of a gearbox just having a pinion and a gear. So, this is N1 T1 and N2 T2. So, there is something, if I measure the vibration of this gearbox at one of the bearing locations where I have put a transducer here, and predominantly you will see a very important component which is known as GMF. GMF stands for gear meshing frequency, and which is nothing but number of teeth in a gear times rotational speed of the gear. Now, what happens if the gears are meshing? This is N1, T1, N2, T2. If I, and because of load, these signals are modulated. And as you recall, modulated signals in the time domain will give side bands in frequency domain. So, characteristics of gear vibrations in the frequency domain is actually presence of side bands. This is the GMF, and in this case N2, T2 being large, N2 will be smaller. So, this distance is nothing N2 by 60, where N is in RPM, and this will be N1 by 60 and so on. So, I will have in a gearbox spectrum, vibration spectrum, I will have GMF plus minus N1 by 60, GMF plus minus N2 by 60 and GMF. Okay. So, what happens? The amplitudes with the increase in the severity of the defect, let me write this down, with increase in severity of gear defect, the amplitude of the side bands would increase. So, one could be monitoring the amplitudes of the side bands of the gearbox and see. Okay. So, this is another 3-stage gearbox in a plant. This is some view which I am going to give you. You can see there is a motor here, and motor is along into the plane of this projection here, but you see there is a 90-degree turn in the power direction. So, we have a strong bevel gear in this gearbox, and this is the same example you recall in one of the classes I was mentioning that how misalignment can occur. You see these here, these shims and the foundations have corroded because this was very close to a C, this is a port, and the gearbox foundations corroded, and this gave rise to misalignment, and there is a lot of vibrations in the gearbox. But coming back to my discussion on gearboxes, so we can measure the vibrations near the bearings and on the foundation of the gearbox and so on. But actually in an actual gearbox, the problem is in the while you are doing vibration monitoring, there are, and on top of it I cannot separate the bearing vibrations from the gear vibrations. So, there will be a lot of frequencies, and in this you have to detect the side bands. Okay. And that is why to detection of side bands, either we have to do what is known as the demodulation, or to do the classify a family of sidebands or group a family of sidebands, we have to do what is known as the subsystem analysis. We discussed about subsystem analysis earlier, and so subsystem analysis is used to monitor gearbox signals and group a family of side bands. And I have been always asked this question, that how do you identify which gear is defective in a multi-stage gearbox? Well, the access to you is the bearing locations. So, all you do with a common point of vibrations x, you can measure the roving y at location 1, 2, 3, 4, 5, 6 and find out the coherence gamma square x y between these signals, okay, and this value will be somewhere less between 1. So, if it is close to 1, you can know that a vibration at a particular location is only because of that. So, you can find out the strongest contributor to the measured vibration by what is known as coherence analysis. Okay. And such analysis people do follow in condition monitoring. So, what are the causes of gearbox faults? Excessive load, fluctuating speed and torsional vibration. Why does fluctuating speed occur? By now, you must have got an idea why fluctuating speed occurs. One is the prime mover. It could be fluctuating power supply in terms of the frequency, if there is a case of an electric motor. So, this will all give rise to torsional vibrations, and then there will be excessive vibrations. Lack of lubricant, because if you see the gears which are mating, there is always contact. So, if this lubricant is not there, there will be high heat generations, and then there will be a lot of wear. Then if there is presence of foreign particles in a gearbox, I have been to plants, when we open up the gearbox, I see on the slide on the sides a lot of sludge. Over the period of time, the gearbox was not overhauled, and a lot of this sludge which has been formed because of the debris and the oil get deposited, and they become like a grinding media, and they wear out the particles. And as you know, these surfaces have to be very hard, and they undergo heat treatment. And if you look at the stresses here, the stresses at the maximum at the root. So, there could be cracks which can develop, and if this go unnoticed, eventually they may fail. So, even another new technique people have used is something called acoustic emission, which I am going to discuss in a later class, that how acoustic emission can be used to find out even defects in gearboxes. So, these are how gearbox faults occur. So, types of gearbox failures: pitting, cracks at the root, Scuffing is what is known as breaking of the oil film, a bearing fault, debris detections, coupling faults and overheating. So, these all are responsible for the bearing faults. So, some of the signal analysis techniques which are used, I can still do kurtosis because there is a lot of peakiness in the signals, frequency domain analysis, sidebands due to modulations, and modulation occur because of amplitude defects. So, to detect sidebands we can use substrum, we have discussed this before, and because there is a lot of transients occurring and the signals are not stationary, one can do what is known as the time frequency analysis to detect impacts like wavelets. So, this is even in a normal gearbox out of the rig in the laboratory which we saw, we can see such gear meshing frequencies coming up, but the intensity of the sidebands would increase when the gearbox warms out. Okay. So, and to detect the particular gear, all you require is the substem analysis given in Q frequencies, and if you see 4.8 milliseconds or 9.6 milliseconds and there is an amplitude. So, this means the gear which is having a time period of 4.8 milliseconds is severely getting affected. So, if I monitor this amplitude over a period of time in a gearbox where there are a lot of vibrating signals, I can monitor at these Q frequencies and find out the faults in the gearbox. So, this is how gearbox defects can be found out. Of course, there are other methods like thermography, motor current signature analysis, etc., which we will discuss subsequently, and some of them are discussed in my book. Thank you.